Okay, today we're going to begin talking some more about permutation groups. So the permutation group S of x, that's just all mappings from x to x that are one-to-one and onto. If x equals, if the size of x equals n, we can think about x. Might as well, since we're only interested in the elements of the group, we might as well just label them as numbers, 1 through n, symbols. And we write S sub n for the permutation group on an n-element set. That's called the symmetric group on n letters. What is the order of Sn? Sn equals n factorial. We prove that in the notes. A sketch of it we have is just, you can think of alpha. For each alpha in Sn, alpha 1 goes someplace. So let's just say alpha 1 equals n. It's got to go someplace. So in that case, we sort of have n choices. And then you can look at alpha, what's left, alpha 2, alpha 3, up the way to alpha n. This is really how many permutations. This has Sn minus 1 permutations in it. Because we have n minus 1 symbols, and by the inductive hypothesis, if we think of induction, we would have then the order of Sn is n minus 1 factorial of Sn minus 1. So the order of Sn is you have n choices for what to send alpha 1 to, and then times n minus 1 factorial ways to permute the rest. And that's just n factorial. So that's a sketch of it by induction. Certainly a one-element permutation, if there's only one, the only permutation is just the identity permutation. So we can look at some groups. We sometimes represent a cyclic a group on rotation. So the way we're going to write, we write alpha I for alpha applied to I minus 1. So this will be a little bit different when we multiply the permutations. We think of sort of, since we go from left to right in English, that's how we'll multiply the permutations as well. So we won't be using function notation as much as we'll be using this notation. But this I alpha means put I into the permutation alpha. So we can have a cyclic permutation. If alpha is a permutation, we can represent, well, cyclic, I meant a matrix. So you put 1, 2, all the way up to n, and then below it you put the value of 1 on the permutation, the value of 2 on the permutation, up to the value of n on the permutation. So let's look at some groups S2, how many permutations there are. There's the identity permutation, and the only other permutation would send 1 to 2 and 2 to 1. And that's a pretty bulky notation. We'll soon move forward onto how to decompose them in a more compact notation. S3 As always, we have the identity permutation. We could also map 1 to 2, 2 to 1, and keep 3 the same. We could map 1 to 2, map 2 to 3, and 3 would have to go to 1. Map 1 to 3, 2 to 1, 3 to 1. Let's see, 2, 3, 1, 3, 2, 1. Map 1 to 3, 2 to 1, 1 to 3 to 1. Something's wrong there. 3 to 1. 3 would have to go to 2. And finally, map 1 to 1, and map 2 to 3, and 3 to 2. 1, 2, 3, 4, 5, 6. So we have 6 elements in S3. Now, multiplication of permutations is really no standard way. Different books and different approaches will do the same thing. We're going to go a little bit opposite from pre-calc, the way we compose functions. We're going to think of calculus, not calculus, we're going to think of the way we lead left to right. So what we do is we put the element on the left, and then the first permutation that's going to hit it is the one on the left. So alpha times beta we would represent as 1. 1 would go to, we put 1 into alpha first, and then put that into beta. So that reads a little bit different than that alpha circle beta if you were thinking of function composition. We'll use a slightly different notation here. And then 2 goes into alpha, and then beta, etc. So a typical element at I would stick I into alpha and then beta. And all the way up to n, and stick n into alpha and n into beta. So this really means we do alpha first in our multiplication, left to right, the way we read it, not necessarily the way we work with function composition in pre-calculus and calculus. So let's look at some examples. Let's look at 1, 2, 3, 2, 1, 3, times 1, 2, 3, 1, 3, 2, this permutation. So where does 1 go? So again, we start here, we hit this permutation first. So 1 acts on this permutation, 1 sends 1 to 2, and then the next permutation sends 2 to 3. So 1 would go to 3. 2 would go to 1, and then 1 would remain fixed by 1 by this permutation. So 2 goes into alpha first, so this permutation first, it goes to 1, then it goes into this 1, it gets into this permutation, it stays at 1, so 2 would go to 1. So we have a permutation, 3 better go to 3, 3 better go to 2. First action on 3, it goes into 3, then that result, 3, gets here and is mapped to 2. So we have that. And then we'll look at the other way of multiplying them and see what happens. We would have 1 would go back to 1 first, and then that 1 goes to 2, so 1 goes to 2. 2 would go to 3 under this permutation, and then 3 is fixed. 3 stays at 3. So 2 would go to 3, and then finally we better get 3 has to go to 1. So 3 would be mapped to 2, and that result 2 gets mapped to 1. And so these are not equal. And so S3 is not abelian. And it turns out what we have is Sn is not abelian. For n greater than or equal to 3. Because imagine in this permutation, and I have this in the notes, we just put 4 goes to 4, 5 goes to 5, 6 goes to 6, etc. We would still have a different permutation, right? Even though the product of these two permutations and these two in the reverse order would all send 4 to 4, 5 to 5, etc., all the way up to n. They don't agree here. For instance, this one sends 1 to 3, the other sends 1 to 2. And remember, with functions, for functions to be equal, they have to agree on every value. So we want to get a way to represent permutations more compactly. And so what we want to do is maybe want to look at cycle decomposition. And so one way to do it is you can write a product, write a permutation uniquely as a product of what I call disjoint cycles. Okay, so we have some theoretical things on what these cycles actually are, but let me first apply it to some example. The identity action permutation is the one case that maybe does not have a unique way of writing it. So let's look at this permutation here. What we do is we write what's called the orbit of something. Again, this is in the notes, and we'll maybe talk a little bit about it. What we look at is we take any element and we apply the permutation to that, and apply the permutation again and again and again repeatedly until you see what happens. So let's look what happens here. 1 would go to 2. So we put 1, we start with 1. The next thing would be 2. What happens to 2? 2 would go back to 1. So that would close up the cycle. Right? Think of sort of 1. What would we get if we apply this permutation to 1? We get, if you think of this as alpha, we have 1, and then this is alpha, 1 applied to alpha. And this right here, this one we can think about as alpha squared applied to 1, which would be just applied alpha to this one. And so it comes back, and that's it. And then 3 just goes to 3, right? So if alpha is applied to 3, we get 3. Alpha squared is applied to 3, we still get 3. So that's what these cycles are. They're ways to, any element in a cycle is connected to another element by repeatedly applying alpha. So in a cycle, you can get from 2 to 1 by alpha. But disjoint cycles, you can't get from one to the other. And then usually it's customary we skip the single cycle. And that's unique, except in the sense, maybe what if you wrote it as 2, 1, but that's really the same permutation. It sends 2 to 1 and 1 to 2, right? 2 goes to 1, and then 1 comes back around and goes to 2. 1 goes to 2, and then 2 goes back to 1. So really, any cycle, they're unique, but you can start it at any point. So if you had let's maybe look at another cycle. How about this one? So we start with 1. 1 would go to 2, so we indicate that. Then 2 would now go to 3, and then 3 would then come back around to 1. So we could write it that. We could also write it as 2, 3, 1, 3, 1, 2. The key thing is the order. 1, 2, 3. 1, 2, 3. 1, 2, 3. So when we say it's these are treated the same as a cycle. So it's unique, and it's unique up until the order of cycles. So unique up to possible rearrangement of the order of the cycles. This is a cycle here. So let's look at an example. So take alpha is 1, 2, 3, 4, 5, 2, 3, 4, 5, 1 as an element of S5. So let's pick any one. We can start, usually start with 1. You don't have to, but customarily I'll start with 1. 1 would be mapped to 2. What happens to 2? 2 is mapped to 3. So we write 1, 2, 3. 3 is mapped to 4. 4 is mapped to 5. 5 comes back around and is mapped to 1. So alpha has a representation as a single cycle. And again, what makes it a cycle, any element in here we can get just by applying alpha, right, to any other. So let's take 4 and 2. So 4 we apply alpha once. 4 put into alpha takes us 5. 4 put into alpha squared would take you to 1. 4 put into alpha to the third power would take you to 2. You can also get the inverse cycle pretty quickly from this way. You can just write alpha inverse would be 5, 4, 3, 2, 1. Why is that? Let's do alpha first. 1 would go to 2, but then 2 would go back to 1. So the net effect would be 1 to 1. So there's a nice way to represent the inverse. When you have cycles, you can also take the inverse fairly easily. Just reverse the order of the cycle. So let's look at another example. Suppose we take beta 1, 2, 3, 4, 5, 5, 4, 1, 2, 3. And we write it as a disjoint cycle. So beta is just, we'll start with 1. 1 would go to 5. Then what about 5? 5 would then go to 3. 3 would come back to 1, so that closes the cycle. What about 4 and 2? So 2. 2 would go to 4, 4 would come back around, and that would close that cycle. So you've got the cycle decomposition of it. And then if you want to take beta inverse, you can just take the inverse of each cycle. So you could do 3, 5, 1. And then 2, 4. The one thing you notice about 2, 4, we can rewrite that 4, 2 and 2, 4 both represent the same permutation, right? 2, 4 is a permutation that maps 2 to 4, 4 to 2, and leaves everything else fixed. That's the key thing. The elements that are not in the cycle, if we apply the permutation to that element, if we don't see them in, if you don't see them if you just have a single cycle, the elements not there are fixed. So it's sort of shorthand. You don't bother to list all the elements. necessarily. But again, in this example, we have listed all 5. So again, what a cycle really is, you start with some number A, and then you look at alpha applied to A, alpha squared applied to A, alpha cubed applied to A. And this list goes on forever. You can always take it, but we can write it as alpha applied to A, alpha squared applied to A, etc., alpha to the K applied to A. Well, actually, alpha to the K minus 1, where K is the least positive integer, with alpha to the K taking A back to A. Certainly that has to happen, right? Because alpha to any power has to be one of the symbols in the set X. X is a finite set, so there's only finitely many symbols in X. So eventually, K can be any integer. Eventually, at some point, we've got to hit an integer when we exceed the number of elements in the set where there's no place left. A has to land back on itself. And that's called a cycle. So that's how we get the cycle decomposition. Or that's how we get the disjoint cycle. Essentially, we take an element and we keep applying the permutation to it, and apply it again, and list the order and what happens. So the number that comes the symbol that comes right after A is alpha applied to A. The symbol after that is alpha squared applied to A, which is just alpha applied to A, so that alpha A. Then alpha cubed is just alpha applied to A alpha squared. Okay, and if we write it as 1, n is a cycle of length n. And so formally, in some of the proof technique, we can think of this list as, we do this script O sub alpha of A, and that's basically going to be A alpha to the K for all integers K. So you think if that's what an orbit is, if we start with A and list them in order, and once we get A, we come back and close it, that's how we get a cycle decomposition. And it turns out these orbits, these are equivalence classes. So that's how you know the cycles will be disjoint in this way. You can't get two cycles are either exactly the same or they have nothing in common. So like we could start with, in this one we could have started with 5 and looked at the orbit of 5. 5 would go to 3, 3 would go to 1, 1 would go back to 5, and so we write the cycle that way, but these two are the same as the set. In terms of the set, what do you mean by same? The order, 1, 5, 3, that's the key. That's not equal to 1, 3, 5, right? So the order you list them is important, not where you start with, but once you pick a start, 5 has to be followed by 3, 3 has to be followed by 1, and then wrapping around, 1 would have to be followed by 5. So you may ask,
is this, doesn't matter the order. Can I write it as 2, 4, and then put this cycle? This is the order of the disjoint cycle. And it turns out it doesn't matter because disjoint cycles commute. Let me just say this kind of fact that if you look at two orbits for two different elements under the same permutation, either the two orbits, which are cycles, are the same, or the two orbits have nothing in common. Again, if we think of the orbit as a set, we need to list that. So. Okay, so let's show that disjoint cycles commute. Okay, so a proposition: disjoint cycles alpha and beta commute. Alpha beta equals beta alpha. Again, where alpha and beta have no elements in common. So let's see why that's the case. Okay, so if there's no common elements in the cycle, we can think we can split X into sets disjoint A and B, where every element is in either A or B in the union, and A intersects B is the empty set. With a following property. So what property do they have? Remember, if we don't see an element in a cycle, that means it's fixed. So what we have is either, the way I chose A, for all A and A, A is in alpha of A stays in A. So either alpha of A is either fixed by alpha or it's in the orbit. And if I put beta of A, I would just get A. So if you think about, include the elements that we see in alpha and leave out the elements that we see in beta. Some elements might be neither. We can arbitrarily put them in A or B, which it would still be true, right? Because if we picked an element that neither alpha or beta have in them, in the cycle decomposition, then we have this, certainly, and alpha A would be just A, so if we pick A and A, alpha of A would stay in A. And for all B and B, beta applied, if we apply beta to B, that's going to be an element of B. So we think of it, we put everything we see in the cycle, in the cycle beta in B, and everything in A we leave out because we know they have nothing in common. So if you're in the cycle, if you're an element listed in alpha, you can't be in beta, and that means beta must fix you. So we can do this, there's maybe some choice as to where the elements that are in neither go, but they'll hold in either case. Suppose that element in A, the element we didn't see in A, we didn't want to put it over here, we put it over here. We think of it as an element in the set B, called B. So B is not an element of, I have to change one thing. B is not an element of alpha. So we have B alpha equals B. Right, yeah, so that was a mistake there. B, we think of the elements that we see in beta, that means we don't see in alpha, so when we apply alpha to those elements, they fix it. It doesn't do anything. And then everything else either is in beta, so we can put it here, or if we just throw it in B, B of beta would be fixed as B, but that's also an element of the set B. So anyway, that's the breakdown. The elements that are in alpha, that we see in alpha definitely go here. The elements that are in beta go here. The elements that are in neither, it doesn't matter. We can put them someplace. It will still be a true statement. So let's see what happens. Then for all A and A, what happens? Let's look at A, alpha, beta. Well, A is an A, so A alpha is an A. So this is an element of A. But then if it's in A, that means beta doesn't do anything to it. So beta of that element is fixed. So it would just be A alpha. But let's look at, let's see, A alpha. Now let's move back, but A is in A. So we can put a beta in front of that. A is the same thing as A beta. So again, this we think of, this is since A alpha is an element of A, if we apply something in A to beta, nothing happens, so we still get A alpha. But here we're thinking of A being an element of A. So again, if we apply beta to an element of A, nothing happens. So read it this way. A is the same thing as A applied to beta. What about for all B? So again, alpha beta equals beta alpha for elements of A. What about for elements B? If we look at B alpha beta, well again, by definition of the way we set it up, B sub alpha is fixed, so that's B But what do we know about B sub alpha? By assumption, B applied to alpha, this is an element of B. So anytime we see an element of B, we can just slap an alpha in front of it, or just put it into alpha, nothing happens. So this says alpha beta agrees for every element. Alpha beta of B is the same as beta alpha B for every element of B. This says alpha beta of A is the same as beta alpha of A for every element of A. So what we have is basically, for any element of X has to be one of these two sets. And so the permutations agree, alpha beta, beta alpha agree on every element of X. So they must be equal. So disjoint cycles commute. So when we write the product of cycles, it doesn't matter the order we had written before, because we always write a permutation as a product of disjoint cycles. This proposition tells us it doesn't matter in which order we list the disjoint cycles. Let's look at another permutation. Maybe before I go that, I think there's one more example in the notes that I didn't do earlier. I don't think I did a gamma. And again, I'll think of the cycle decomposition. Now that I introduced that terminology of orbit, let's see how we can maybe write it here. So we basically would have 1, and gamma of 1, which is gamma of 1 is 2. Then gamma squared of 1, but that's just the same thing as gamma of 2, which is back to 1. So that would give us the cycle 1, 2. And that's an orbit. Then the next set would be 3. 3 would go to 4. So we have 3, and then we look at gamma of 3 would be just 3. So 3 goes to 3, we just write a 3 here as a disjoint cycle. But usually, unless it's the identity, which fixes everything, we leave off the 3. Right? Why put it there? If we don't see a number, then we know that number is mapped to itself by the permutation. So that's a third orbit. That's the orbit of 3 under gamma. What about what's left? So we've got 1, 2, 3. Let's look at the orbit of 4. Oh, I misread this. I'm sorry. This is 4. Looking at an angle here. 3 would map to 4. So then we keep going then. So we don't cross this out. We would put 3, 4. Then the next element would be 3 gamma squared. But gamma applied to 3 is 4, so that's 4 applied to gamma. That takes you back to 3. So that will close it up. That's your second orbit. And finally, the last orbit, 5, and then if we look at gamma of 5 is just 5. So we close it up, so we put a 5 here. But we wouldn't write that. So we would represent gamma as 1, 2 times 3, 4. Oh, so we can see this by maybe multiplying some cycles. Let's look at another example. Let alpha be 1, 2, 3, 4, and beta be 5, 6, 7. Again, these two are disjoint. All three of these are points. So what I say that alpha beta should equal beta alpha. So let's kind of put it in matrix form just to see. So, or maybe write it in cycle notation and see what happens. So let's look at, well, let's do it in 1, 2, 3, 4, 5, 6, 7. So let's look at alpha beta. Remember, we act on from the left, so we hit alpha first. So 1 would go to 2, and then 2 remains at 2 and 2. So that's just it. 2 would go to 1, and that would be it. 3 would go to 4. 4 would go to 3. And that's it. Then we move up here to this product. 5 would go to 6. 6 would go to 7. 7 would go to 5. So that's alpha beta. let's do beta alpha, which is 5, 6, 7, 1, 2, 3, 4. So let's write it as a matrix. So what happens to 1? So 1 goes to 1, 1 goes to 2, and then 1 is fixed by that, so 1 ends up going to 2. 2 stays at 2, then 2 goes to 1, then it remains fixed. See how there's nothing in common with the cycles at this joint. Once you get the cycle that involves a number, like say 6, we do this first. 6 would go to 7, and that would be it. So 6 would go to 7. What are we up to? 3. So 3 is fixed. 3 still stays to 3, then 3 goes to 4. So the net effect is 3 go to 4. Again, when we multiply with the way we read. We start left to right. 4. 4 gets fixed, 4 gets fixed, 4 goes back to 3. So that would be 3. 5. 5 goes to 6, and that's it. We've already done 6. How about 7? 7 goes to 5. 5 remains at 5. 5 remains at 5. So we have the same. So what is an order of a cycle? Remember, this is a group, so we talk about the order of an element of a group. So it turns out the order of a cycle is just its length. Right? Does that make sense? If you think about something in the cycle, why would this have order 3? Well, if you apply alpha 3 times to 5, it goes back to 5. If you apply, or this cycle, I guess it's just beta. If you apply beta 3 times to 6, it goes back to 6. If you apply beta 3 times to 7, it goes back to 7. If you apply beta to 1, beta of 1 equals 1. So certainly applying beta 3 times to 1 will, the other elements that we don't see in the cycle are fixed by any power of beta. So again, a K-cycle is a cycle with length K. So K equals, we put a 1, AN, A1, A2, all the way up to AK, where K is the least K is the least positive integer that takes A alpha, multiply on the left, right? So A1, call this alpha, where alpha to the K takes you back to A1. And just intuitively, if it's K steps to come back here, it would be K steps for A2 to come back to A2, etc. So my claim, if alpha is a K cycle, then alpha, the order of alpha as an element of the group is K. So in particular, alpha to the K equals, use epsilon here. Epsilon is the identity permutation. So the order of a permutation as an order of groups, if it's easy, if it's a cycle, the order of that permutation is just the length of the cycle. Also note just a little thing. Usually for E, we just sometimes write E, or sometimes we just write 1. E, that's the one case where usually we leave out the 1 cycles. But you can think of a permutation, the identity permutation is just a whole product of 1 cycles. 1, 2, 3, 4. So we can't leave out all the 1 cycles, because that's what the identity is. It's all 1 cycles. So we just put a 1 there. So really you could also write 3. You can really put any single cycle there. That represents that the identity fixes 3, and then everything we don't see there it fixes. So it fixes 3, it fixes everything else. And maybe we'll prove the claim, but let's just also say if alpha and beta are disjoint cycles, then the order of alpha and beta well, you wouldn't want the length, you wouldn't want to necessarily multiply them. It would have to be the least common multiple. So we can maybe sketch a little bit of that first proof. In this one, we just kind of, just by way of example, if you think of, say, the order of this was 8 and the order of this was 6. That means every 8 times you hit alpha, you would get the identity. And every 6 times you applied beta, you would get the identity. And then, remember, they disjointly commute, so if we apply the product of alpha, beta, n times, that's the same as applying alpha n times and then beta n times. That's where the disjoint cycle comes in. So if alpha had order 8 and beta had order 6, the least common multiple of 8 and 6 is 24. And so if you raised it, you couldn't go a full 6 product 48 times, but if you went 24 times, then it would be a multiple of 6, so beta would map everything to the identity, and it would be a multiple of 8, so alpha would also be the identity, map everything to itself. So let's maybe just look at the claim, the proof of the claim. So again, we've seen that we have A1 alpha to the K equals A1. For I going from 2 to K, we have AI equals A alpha to the alpha K minus 1, right? That's what A2 was alpha to the 1. A3 was we hit alpha, we hit A1 squared, sorry, A1. So we have that. So what we get, so this means, let's stick each of these into alpha to the K. So, this is I, sorry, this is not K. Oh, the last one would be K, n minus 1. This would be alpha to the I, right? The second one would be A1, and we put that into alpha 2 minus 1, 1. The third one, we put the first element A1 into alpha squared. Third element, second, apply alpha twice. Fourth element in our list, apply alpha 3 times. Okay, so now we apply AK, so AI alpha to the K is A1 alpha I minus 1 alpha to the K, or we have A1 alpha, A sub I alpha to the K would be A1, and if we add that together, we can switch the order, alpha to the K, I minus 1. I put here, not sure why I wrote beta. Right, so I'm just copying this over. A1 alpha to the K. But A1 alpha to the K, remember, is A1. So we have AI alpha to the K equals A1 alpha to the I minus 1. That's exactly A alpha. So what do we have? We have for A1 all the way up to AN, we've just shown that alpha I applied to A, stuck into alpha to the K, A sub I, alpha to the K will fix that. It will take you back to A sub I. And for X in X, but not equal to these elements, for different X's in that set, this means take away. X alpha is just X, so we also have X alpha to the K is still going to be X. So if we hit everything in the cycle with alpha K times, we get back, it does nothing, we get that element back. If we hit everything that's not in the cycle with alpha any number of times, we get that back. So the upshot is, for all X and capital X, I'm going to use Y, alpha to the K of Y is just going to take me back to Y. So that really means alpha to the K is the identity. But that just means maybe the order divides. So that tells us the order of alpha must divide the order of K. Must divide K. But if the order of alpha is some S that's strictly less than K, we have A1 alpha to the S would have to take you to A1, anything alpha to the S. Is that right? This really means alpha to the S would have to be the identity in particular, right? Anything raised to its order gives you the identity. So this contradicts. Remember the way we get the length of the cycle. K is the least positive integer that takes A1 back to itself. So that proves the claim. So we can't have the order being less than K. So it has to divide K. So it has to equal K. Right? S basically divides K, but S can't be less than K, so that has to mean S equals K. So we'll stop at this point and begin to look at a different way to break down permutations. Not with disjoint cycles, but a different way. Let me just make another statement as well. Just in the natural extension of my fact, another fact. If alpha equals alpha 1 up to alpha, say, t, where alpha 1 through alpha t are disjoint cycles that are the cycles that have nothing in common with any of the other cycles. Just like if there were two elements, the order of the product would be the least common multiple. If there's t of these elements, the order of this product of all these permutations is just the least common multiple of all the orders of the individual cycles. And the orders of the individual cycles are very easy to get because we just look at the length. So we'll close on that and hopefully we'll pick this up shortly.